For the second calculus video, I'm going to attempt to answer the question, what are derivatives? And who cares? So, derivatives are a fantastically powerful tool that we have at our disposal in physics. Before we get to this question though, I'd like to warm up by practicing some things that you saw in last video. And my question for you is, find dy dx, that means find the derivative of the function y as a function of x if y is equal to 3x to the third plus 12x. And now's the point you go back to the table that we created last time. Looks something like this, and maybe you've got some other stuff written on it, and you try to differentiate this function right there. You should pause now and actually do it. Pause. Now. Seriously. This is your last chance. Okay, good work. I hope that you differentiated this to find y, let's see, dy dx should be 9 times x squared plus 12. So if you have this function and you want to know its slope at any time along the function, at any location, its slope will be given by this function. And all you have to do is plug in where you are and its slope will be given to you. Dang, that is really powerful. Maybe you're not convinced yet. I need to talk a little bit more about this d dx. This thing right here is called an operation, and it operates on something. Operates on something called the argument of the operation. And the interesting thing about derivatives is it's no longer just taking in. It's no longer like, this would be the squaring function. Here's a simple example of a function. If you square 1, you get out 1. If you square 3, you get out 9. And if you square -2, you get out 4. The squaring operation is a little black box, you can think of it like this, that spits out something when you put in something. But all the somethings are all numbers. And all the outputs are also numbers. But if you have a derivative, d dx, you can put in a function like x, or x to the third, or sine of x, and it will spit out an entire function. You have to understand this idea of a function. These things have an infinite number of values because you can plug in any value for x. And the derivative don't care. The derivative is just like, I'm going to differentiate that, no problem for you. X, its derivative is 1 all the time. X to the third, its derivative is 3x squared. And the derivative of sine x is cosine of x. So these are functions. Get another color up in here. And the output is also functions. So this is a functional operation, and this is just an arithmetic operation. Functional operation. Now we're getting much more complicated than we were in algebra, algebra 2, that sort of thing. Differentiation is fantastically awesome. So what I want to do now is throw a couple more derivatives at you. I want to give you the derivative of this function right here. You've seen it already, but we need to make it a little bit more concrete. If I've got this function right here, and let's say that the function of x is y, and it's 1/2 x squared. If we differentiate that sucker, we're going to get let's see, this is y as a function of x. If we differentiate it, we're going to get this function right here. I hope you'll forgive me for simply writing diff. This next function is going to have a slope of 1 the whole time. So I'm going to write this as d, it's the derivative of the function of x. Let's make this lowercase. I don't know what I was thinking right there. If I'm taking the derivative of the function of x with respect to x, that's what we mean when we write dx in the denominator. This is the same as dy dx, just kind of getting some language out of the way for you. And in fact, this answer here, I've got to say the answer here is equal to x, because this function is y equals x. That function is y is 1/2 x squared, and this function is y is equal to x. If I differentiate one further time, I'm going to get something that has two derivatives. Check this out. This I can write as d squared of y dx squared, because it's d dx of d dx of y. So there are two dx's in the denominator and there are two d's up top. That means I'm operating twice on the function that I have up here to get the second derivative. That's what it's called. And the second derivative in this case, well, check it out. We got a constant slope, and that slope is always 1. And so in this case, I'm going to write here, it's 1. The second derivative of this function is 1. You can differentiate and differentiate and differentiate, and look at this. A lot of the time, if you continue differentiating, you get simpler and simpler functions. Our original function was x squared, then we got x, then we got 1. If I were to differentiate one more time, this will be crazy. Since it's crazy, I'm going to put it in purple. d3y dx to the third. Well, if I differentiate 1, its slope is always the same, and its slope is not slopey. It doesn't change as x changes. So this makes simpler and simpler. Many functions you'll find eventually have no slope at all if you continue differentiating them. In physics, we can talk about maybe position. And the derivative of position is, of course, velocity. And the derivative of velocity is acceleration. And the derivative of acceleration, the derivative of acceleration is called jerk. And that's reasonable, right? When your acceleration is changing, you feel kind of jerked or lurched out of where you've been. After jerk comes snap, which is kind of a reasonable feeling also. If you continue differentiating, then you get crackle after that. And if you differentiate one more time, you get pop. And well, it goes on from there, but I think that's a good place to leave it. So I want to tell you about a function that has a very interesting derivative, and that is one of my favorite functions. Let's see. This cool function starts out just above, and it goes like that. And this function, let's set up our axes here, this function is called y is e to the x, the exponential function. And you'll like it too. If we differentiate, let's differentiate that sucker right now. Let's just do it. Notice that the slope is very small over here, but it's positive. And right here, the slope is getting bigger and bigger and bigger, and as we go further over to the right, the slope gets bigger and bigger and bigger. Turns out that this has a very... You know what? I think I'd like you to try that. Can you try the calculator trick that I've taught you in class and find the derivative of that function right there? Try to overlay other functions on it, or notice what you can. Pause. Okay. This function, as I hope you noticed, is, well, let's say if I've differentiated, then now I'm talking about dy dx. Well, dy dx is also e to the x. That's awesome. Let's make it a little bit more awesome. If we have our little table here where we say y and we say dy dx. We know, in general, we know c times x to the n is going to be n times c times x to the n minus 1. And, ooh, I could give you some other challenges. No, here's what I'm thinking. I'm thinking we could also throw up a c times e to the x. Whoa, c times e to the x is going to be, well, its derivative is still c times e to the x. Okay. One more thing that we'll need in physics. I'll take this right here and go just a tiny bit further. Another relationship that we need is what happens if we have an a up there also. And this is really wonderful. We're going to get, we're going to have to differentiate this. Is some wonderful process called the chain rule, and we're going to get c times e, well, let's not write it like that. We're going to get c times a times e to the ax, where a is the coefficient of x up there. Okay, so we just drop an a down, no problem at all. One of the cool things, the reason that we're doing this is to learn about what the derivative can do for us. So let me throw a function at you, and here it is. Here's my funky function. And this is y is some function of x, and here's x. What if somebody asked you, if they gave you just the functional form, they didn't show you the graph, what if they asked you where this function has a maximum? Now obviously it's got a maximum right up here, right? Who knows where that is? Who cares, right? That's way, probably infinitely far out. It looks like it's getting bigger all the time. But there's a maximum right here also, right? And they could also, we'll have to call it local max.
Please, Peterson family to the desk.
And this sucker right here is a local minimum. Alright, so we can find this local max and the local min using the methods of calculus. Because what do you notice? What do you notice about the slope of the function? Right there and right there. Slope, grab a piece of paper, trace along, slope is big, slope is getting smaller, slope is exactly 0 right there. Slope gets smaller, slope gets bigger, boom, slope is 0 right there also. So we can write this general maxim right here that says slope is 0 at local max and local min. Slope is 0 at a local max and at a local minimum. Okay, and this makes sense because when you're at the top of your path, whether it's local or global top of your path, you have to stop and turn around, which means your velocity is 0. So if this is position and this is time, and we've got a platypus rising, 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 before it goes down, it has to stop. And we can mathematically find the time when it stopped by saying that if this is position versus time, the slope is velocity as a function of time, and the velocity is 0 when the platypus stops. So that defines a local maximum or minimum. The question is, though, is it a local maximum or is it a local minimum? If you have a platypus that's being driven up and down and up and down, maybe platypus on a roller coaster, that'd be pretty awesome, then you're not going to know when you find that the derivative is 0 And instead of slope, I'm going to say derivative is 0. When you find that the derivative is 0, then you're going to be able to say that it is either a local max or a local min, but we don't know yet how to find out whether it's a local max or a local min. So the example goes like this. Nolan Ryan comes out of retirement and he finds a small duck-billed platypus. And he throws the platypus up into the air at 30 meters per second. And the initial height of the platypus is 2 meters. That's going to be the initial height, and this is the initial velocity of the platypus. So we have to ask ourselves, when does the platypus reach its maximum height? So another thing that we know is, let's call it 10 meters per second squared, because I didn't bring my calculator today, is the acceleration of the platypus the entire time. So we can work this in the traditional way. There are equations to solve this, but let's pretend we know no physics at all, and we have only the calculus that we've just learned. We know also that the slope is 0 at a local maximum and at a local minimum. That's when the derivative is 0. So let's write ourselves the equation. We can say that the final position, or that is the position at any moment, so I'll just write x, is equal to where you started plus the initial velocity times time plus 1/2 the acceleration times time squared. You know this equation. So to translate it into the math form that we've got right here, we say y is equal to y naught plus, no, it's better if we don't do it with variables. Let's say y, because remember, y is our dependent variable and x is our independent variable in math, but in physics, x is our dependent variable and t is our independent variable. Time marches on and we do things within it. So I'm going to write y is equal to 2 meters plus 30 meters per second times time minus, check this minus sign right here, that's a t, minus 5 meters per second squared times time squared. If I'm proposing, if we take the derivative of this function right here and set it equal to 0, we will find the time when the platypus reaches its maximum height. So let's say dy d, oh shoot, we were supposed to make this into math form, so I'll put an x there and I'll put an x squared there. Okay, dy dx is equal to, what's the slope of 2? The slope of 2 meters? That's 0. And the slope of 30 meters per second times x? That's 30. And the slope of negative 5 times x squared, now this is x squared, so we're going to lose, we're going to have to lower the power of x, and we'll multiply the 2 by the 5, so we'll say minus 10 times x. And we want dy dx equals 0. This is setting the derivative equal to 0 to find the time when the platypus is at its maximum height. So we say 0 is equal to 30 minus 10x. And we can solve this by adding, well, let's subtract 30 from both sides. We're going to get negative 30 equals negative 10 times x. We'll divide both sides by 10. Let's divide both sides by negative 10. Go all out, right? And finally, we get that x is equal to 3. So I propose, translate back into math, back into physics terms, 3 seconds is when the time is at the maximum. So this is not a general equation. I can write little maxes right here. X max. Well, it might be a minimum also, and we'll talk about that in a minute. But that's when the platypus reaches a maximum height. If I know that the platypus reaches a maximum height at 3 seconds, how can I find out how high up the platypus is? Well, we have this equation for how high the platypus is at any time. And we can use, let's use, the time is 3. So the position of the platypus is the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. And I'm going to plug in to find how high the platypus went. So let's take this equation, and I'm gonna, because I'm plugging in this time right here, I'm going to find the maximum height because this is T max. Watch what happens. Plug in the initial height, which is 2 meters, plug in the initial velocity, 30 meters per second, and I have to multiply that by 3 seconds. And then I'm going to, remember I can subtract -5 meters per second squared. That's half of the acceleration of gravity. And then I need to multiply it by 3 seconds, and I need to multiply it by 3 seconds. That's the time squared in that equation right there. If we throw this all together, see, I didn't bring my calculator, so you have to do what you have to do to get the problem done. This is plus 90 meters, and then I'm going to subtract, minus 45 meters. So that's 45 plus 2. That platypus, it's a very small platypus, that platypus went 47 meters into the air. Alright? So that happened at 3 seconds as well. What I want you to do is, I want you to redo this problem pretending that you don't know any calculus, but pretending you know physics. So use the physics that I've already shown you to find first of all, find the time when the platypus reaches its maximum height, given these initial conditions. And then find the height that the platypus reaches. Now, the final thing that I want to ask you is, do you see another way that we could find whether this is a maximum height or a minimum height? Obviously, you can plug it in and you can look at the number and say 47 meters. Well, 47 meters is higher up than the platypus started. It started at 2 meters, so clearly it's gone up, and this must be a maximum. But the slickest way to do it is to look at the second derivative. Because if we graph the platypus is going up, and then the platypus is coming back down. This is the position of the platypus as a function of time. Here we are back in the physics language where x is the dependent variable and t is the independent variable. So if the position, if we're interested in this moment right here, and this is 3 seconds, we're declaring that to be a maximum. If the position is positive and the initial velocity is positive, what we want is the second derivative, and we know that d squared x dt squared is the acceleration. This is the instantaneous acceleration defined. So we know that this acceleration is in fact negative, and we can say if second, this is just a general rule that you can write down. If second derivative is negative, that means you have a local max. And if the second derivative is positive, that means you have a local minimum. Flower pot. Before we completely abandon derivatives, I want to say just a couple more things. There are some other cool functions that you can differentiate to get really cool results. What if you have a function that does, let's go purple with this because this function's crazy. What if you have a function that does that? Then you can see that usually it's a pretty boring function and its derivative, let's see, y and x here. If I take the derivative of this function, I will find it to be 0 here, and 0 here. But here, the slope gets very big. Very big. It gets gradually bigger, 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 hits a peak, and then gradually gets smaller, 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 smaller. Let's check that out. See if I can draw this. There, that's a nice function. Okay. This is a pretty useful function called a delta function. Actually, a Dirac delta function, but we don't need to worry about that right now. And the final thing I want to show you having to do with derivatives is that you can take the antiderivative. For instance, I could give you a graph down here where this is y and this is x, and I could tell you that the derivative of some function is 1. I'm saying dy dx equals 1. You already know a function that has a derivative that's equal to 1. I'm going to go here and take the antiderivative. And the function that you already know that has an antiderivative of 1 looks like this. This function has a slope of 1 the whole time. But I want to ask you a question. Can you think of another function whose antiderivative is exactly the same? Now remember, when I'm taking the derivative, I'm looking only at the slope of the function. So I guess I'm asking, can you consider another function with an identical slope to that function right there? I can. What about the one that looks like that? Identical slope means that sucker is parallel, right? You want to give me a guess how many functions are parallel to that purple line right there? Yeah, it's a lot. There are a lot of functions that are parallel. So let's be really careful. If I know that dy dx is 1, then the only thing I know about y is it's x plus a constant. So when we're taking the antiderivative, and you'll see the significance of this operation in just a moment if you watch the next video, when I'm taking the antiderivative, I have some uncertainty because I don't know which of these identical parallel lines I actually have. And we can describe these lines as differing by this value right here. Each of them has a different y-intercept. In math class they've taught you can specify a line with the slope and the y-intercept, slope-intercept form, right? So here we are saying that these lines all have different y-intercepts, that's right here, and they all have the same slope, that's right there. Let me write y is mx plus b right here. This is to be identified with that constant right there. This slope is right there, and it's equal to 1 because we said that the slope was equal to 1. So taking an antiderivative always introduces some uncertainty because the y-intercept is not known. In physics, we think of a y-intercept as initial conditions because we're talking usually about position or some other function as a function of time. So that would be the initial conditions of our situation. It turns out many situations are the same even though their initial position is not the same. And we talked about that in the very first video on calculus. Good luck.